Good evening, ma'am and sir. So, in this presentation, I will tell you about the most important pieces of code, explaining the full codes, along with the key important algorithmic importance of the codes. I am going to present in this video. And first, I will start with MAML, that is model agnostic meta learning. Then I will cover iMAML, that is the implicit model agnostic meta learning, that is the key contribution of this paper. So let's begin. So here the thing is, in the red boxes we will concentrate on those lines only. So the MAML code is available on the given GitHub repository for reference, which is mentioned in the link. And that is for the reference that provides a high level API for implementing all meta learning based algorithms using pytorch. And from this presentation I will try to explain the code in parallel to the algorithm, so that it is much easier to digest the algorithm. So first of all, what we need to sample some batches, so that we need to sample some batches. So that amount of batches from our ability over tasks, and we want to sample a batch of tasks in the specific case. So here you will need just probably a couple of lines of code to do that, to do this. So you can easily do it using this loop method, and iterative over all tasks, so that we just sampled from p to p of t, that is like you have a pool of tasks and there is a distribution of tasks, and you are picking iterating over all those tasks, and this is done before in this for loop. Now in this slide we are going to in the algorithm. So basically a sampling k data points, but we don't know to do like we don't know the exact points. So to do this operation, since we are going to just take the support set, we also take the query set at this stage. This can be done later action, but you can easily do it in both of them. So here so for the moment we are using the support set. We are passing these trained inputs to our model. So this is our forward pass, and in the model, and that will give us some prediction into logits, that this represent or y. Okay. And our predictions, then we like, of course, like logits will be converted to the prediction labels, and that is how you will be going to get your predictions. And the first inner loss, you can see that we are still making the turn loss on the data points d, and this represent estimating the inner loss on our support set, right? So we are still meeting their loss with a cross, and so it is just a standard cross entropy loss, not in special or like large loss. So it's obtained here in three targets. Now here uh, now what we want to do, or what we have to do, is to compute the adapted parameters, that gradient descent, like adapted parameters, the gradient descent. This is done in the algorithm with this line here, line number 7. And we can do this in this way in pytorch. First of all, we are going to estimate the gradients on the inner loss on our model, that is meta parameter theta, right? And we want to keep the gradients in graph, so that later on the outer loop, or that is the other loop, our graph is kept in that list, and we are going to get the outer loss, that is the global loss. So like we are not going to reset it, but we are going to accumulate it for the global parameters, because you are actually calculating the inner loss for inner tasks, right? And that will be reporting to the global theta. And we want to define a dictionary of parents, and we are going to iterate here over our meta parameters, and we are going to take the gradients, and what we are just what we are is just it's identical to this. We are going to do a gradient step with a time step size, right? Now, then here in this algorithm, line number 8, we are going to sample some data points, but actually this is our specific set. Just represented by the query points that we already have completed in line 8 of our algorithm. So we don't need to do this, and to be careful now here, because for all the tasks we are doing these other multiple tasks. So in our case, when we are going to do this in our pytorch implementation, we have to call or we have to submit the loss inside the for loop, and we are going to not doing a simple assignment, whereas but we are going to do a sum of all the losses over all the tasks. Okay, so here is your MAML comes, and since we are doing a sum here, we are accumulating in the outer loss all the possible tasks on all the possible tasks, specific losses while we are accumulating, because once you go out from this for loop, your outer loss will contain all the possible losses over all the tasks, and those task specific losses are accumulated. And later on, when we are going to apply our back propagation algorithm or backward pass, we are going to apply this backward pass over all the loss or specific losses. So this is a simple way to do an average or all the possible losses. And once we have done the backward pass, then we are going to apply our optimizer, such that in our case it's just an optimizer with a specific step size. And this is the outer loss that you can see in the line 10, but then the gradient in the fourth step is applied out of this for loop. Now move slowly towards the target parameter value. Default value for that is assumes the learning rate determined by optimizer. So like useful for implementing this program, or what you can say implicit MAML. So we can implement this with the regularization loss, but regularize around the target point, and with the specific choice of our regularizer, that is your LAM, that is 2.0, to preserve the learning rate for inner optimization. Given the gradient step with the outer optimizer using the gradient, assume that the gradient is a tuple or a list of size compatible with our model dot parameters. And if a flat gradient if flat gradient is true, then the gradient is flattened vector, right? And initialize the gradient fields properly. This would initialize all the required variables. So this is the basic idea or overview of the code. By reading the summary, it will be very clear, because in summary I have also mentioned the stepwise procedure, like how this inner tasks are performing and how this inner tasks of meta learning helps to set the global parameters, along with this implicit gradients are helping, such that you don't need your exact path in backward pass, right? I mean, you don't need the same path. You don't need to travel the same path from where you have traversed to reach the to find the your global optimum point. Because when you want to backpropagate, you can actually just what iMAML suggests is like you just visualize these initial point and your final point in a plane and try to optimize in such a way that it comes closer. So this is what iMaml tries to perform. That was all. I will still recommend you to read the summary first and then come again to this presentation. That was all. Thank you. And these are the primary references which I used for program